Before we start the subject strength of materials, it's very important for us to know certain assumptions that this subject follows. So every engineering subject has got certain assumptions. So strength of materials also have certain assumptions. So what are the assumptions? The first one, the material is continuous. You should remember that the material is continuous. What do you mean by that? There should be no voids or cracks. There should be no discontinuity. Okay, so the material is always continuous. Is it practically possible? No, it is also not practically possible, because you won't find any material totally free of voids or cracks. There will be practical materials in which at least some percentage will be voids or cracks. But we assume in strength of materials the concept of continuum, just like we assume it in thermodynamics or in some other subjects. So first assumption is the material is continuous. Again, I am telling these are assumptions, not the reality. We assume things in order to simplify our analysis. So this is our first assumption, and hence it simplified our analysis. Second one, the material is homogeneous and isotropic. What is homogeneous? Homogeneous means when the material, there is a same material throughout. There is a uniform composition and cannot be mechanically separated into different materials. So these are the characteristics of a homogeneous material. If we talk about isotropic, so isotropic means the property values remains same in all the directions. So whenever the property values remain same in all the directions, we call those materials to be isotropic. Just like we have glass, metals, ceramics, plastics, diamond. Make sure diamond is a special case. It's been confused with anisotropic, but it's not. Diamond is an optically isotropic material. I'm just explaining all these things in detail. Why? Because once you have a detailed understanding of a subject, your base and foundation will be strong and you won't fall anywhere. Okay, you'll do good in interview, you'll do good in objective. So the purpose of making such comprehensive and detailed lecture is to make your foundation strong. That's it. We should note something more. If we have talked about homogeneous material, then of course we'll have to talk about heterogeneous material. So materials having non-uniform composition, just the opposite. If you take an example of, say, sand and water, mixture of sand and water, of course there are different materials. Concrete, yes. Cement reinforced with steel. Okay, so these are all heterogeneous materials. Then if we talk about orthotropic materials, so orthotropic materials is also a case of, or rather you can say it's a subset of anisotropic materials. So orthotropic materials, ortho means what? Perpendicular, right? So orthotropic material means here the properties differ along three mutually orthogonally twofold axis of rotational symmetry at a particular point. So what people study is properties differ along three mutually perpendicular directions, but that is not the correct way of saying. Okay, so three mutually perpendicular directions, if you say, then you have to take certain reference. But overall, if you want to speak, then without any reference, you can say that this is three mutually orthogonal twofold axis of rotational symmetry. So once you study this material science in crystallography more in detail, I will teach you, then you will understand what is the meaning of twofold, threefold axis of symmetry, rotational, and so on. But the correct and the most standard definition for this orthotropic material is this. So please remember this. The examples for orthotropic materials, we have wood, crystals, then rolled metals. Then we have heliotropic or anisotropic materials. Very simple. Here the property values vary in different directions. In different directions you will be having different properties, property values rather. Examples, your woods, composites. Okay. Third assumption, there is no self-acting internal forces. Sometimes in textbooks it's written no internal forces. Dear, if there is no internal forces, then where the concept of stress will come into picture? So that is given wrong. You should remember there should be no self-acting internal forces. Self-acting internal forces means that forces which are acting by itself. Just like you have some vibrations which is going to happen. Okay, translational vibration or rotational vibration, all sorts of things, not of its own. If we provide any extra force, there will be some internal force generated, right? But there should not be any prior or initial internal forces present if the body is not disturbed. Okay, so that is the meaning of no self-acting internal forces. But is this practically possible? Still, it's not practically possible, because whichever solid material you take, there will be certain vibrations continuously happening. So if you don't believe me, go to physics department and ask. They will teach you more in detail. Then in fourth assumption, you can say that strength of material follows the principle of superposition. What is principle of superposition? Let's say we have taken any body and there are some different loads acting. Okay, there are number of loads acting. Here I have taken 10 loads, 10 forces. So the net effect will be the resultant one. Okay, also you can say that the resultant strain, that is the net change in the body, will be equal to the algebraic sum of the strains caused by the individual loads. So let's say F1 load, where is F1? Yes, F1 load is giving some strain change. Okay, so it's giving some changes in the body. Similarly, there will be some change in the body due to F2, there will be some change in the body due to F3. So principle of superposition says the net change in the body will be equal to the algebraic sum of all the strains which is happening due to the all individual loads. Fifth assumption we have, that is the self weight is ignored. So here we don't consider all those gravity considerations and all. If we consider, then we are going to make or convert this subject into engineering mechanics. Okay, so that is why that branch has been kept totally different from this particular branch of engineering, right? So here you don't have to consider the self weights of the body. And the last assumption, Saint-Venant principle is valid. Now what is Saint-Venant? Saint-Venant principle is actually a principle given by Mr. Saint-Venant, and we won't study here, because if I teach you here you won't understand anything, because in order to teach this I need to introduce certain more concepts which we have not introduced yet. So we'll study this Saint-Venant principle in the design part or sometime after few lectures. Okay, so these are the 6 major assumptions that your strength of material subject follows. Okay, so with these assumptions we'll proceed with the subject strength of materials, and in the next lecture I will introduce the core part, which is stress. See you in the next lecture. Till then, bye.